person. Okay, this is now recording. Sorry about the noise that you all probably just heard. Oops. So multiplying monomials, that one wasn't too bad. Remember, you multiply each term in one polynomial by each term in the other polynomial for any polynomial multiplication. With monomials, it's very easy because it's one term times one term. What I usually do is I multiply the, I have the word constants there, that should be coefficients. So those are the numbers on the variables. So I multiply those numbers together, then I multiply the variables together. So the example there is 3xy times 2x squared. You see I have it kind of expanded out after that equal sign. All I'm really looking at is I like to keep things straight. So I would look at this and say, okay, I have a 3 times a 2. Okay, that's going to end up with a 6. Then I'll jump to my variables and I'll do them in order. I'll do them in alphabetical order. I'll do the x's first. I have an x, and then I have an x squared. I multiply those together, I get x cubed, yay. And then I have 1y on that left guy, none on the other one, so we just have 1y. So we have 6x cubed and y. Like I said down there, for easier organization, the variables are often written in alphabetical order. That's another thing that can cause problems because I have personally done a ton of problems where I will multiply polynomials together and I'll get one thing with 6yx cubed and one thing with 6x cubed y. And sometimes it just happens to work out to the point where when you're multiplying them together, that's just kind of how you end up writing it. So usually at that point, I'll rewrite it so everything's in alphabetical order so I'm not dizzy trying to figure out which one's which. Like terms are fun at that point. So multiplying monomials with binomials was pretty much the same, except you have to use the distributive property. Literally everything past multiplying monomials together is distributive, right? So you see that 3x times the 5 plus y. You say, okay, it means I have to multiply the 3x times each thing in that parenthesis. I have to do 3x times 5, and I have to do 3x times y. You know, if I was actually writing this on a paper, just imagine those like, you know, lines going to each of those guys, you know. So 3x times 5 would be 15x. 3x times y is great, it's just 3xy. They don't really go together too well, so they just kind of stack up. So sometimes this is also written the other way around. You might look at that and say, oh, that's dumb, why would somebody do that? But again, that's just kind of like, sometimes it works out that way, and that's what you end up with. If you have something on the end of the parentheses instead of in front of it, it does the exact same thing. You would take that, still take that 3x and distribute it into the 5 and the y. Same thing. Okay. So for each example, simplify and multiply as necessary, then state its degree. Okay. So I'm going to write some of these out. Thinking if I could get through this slideshow fast enough, I might just be able to do an entire lesson on systems of equations today. I might be able to. Me thinking out loud. I'd like to. I want to cover that. There's not honestly that much ground to cover on it, but it's kind of tricky. And the other stuff I would much rather have for its own class. just very slowly writing these out on my note page so I can jump over to it. All right. So, looking at this first one, what we have is a monomial times a monomial times a monomial. Remember, polynomials all have like pluses and minuses separating their terms. So you might look at this and say, hey, that's a polynomial. No, it is three monomials multiplied together. Multiplication division just means they're going to stack together, right? So if I have these three, that means I could do a couple of different things. I could multiply two of them together and get one term, and then bring that other one down and multiply those two together. That's an option. I could multiply each one together separately, all at once. That's an option as well. And you can do any combination of those. You could multiply these two together first, bring it down and multiply in that one. However you really want to do it. Personally, I think these types of problems are easiest if I just do it all in one big ugly jumble. Now I am going to kind of expand that out just to be able to show work for one line, but normally I would jump past that. I'm just going to write down like my thought process here. So my thought process would be that like I said in the slide, I usually start with the coefficients and multiply them together. So I know I would have 2, 3, and 7 multiplied together. Then I'd move on to my variables. I'd start with the first one in the alphabet, x. So I have an x, and an x squared. And then I would move on to the next variable, which would be y, and I have one y out of each of those. Now, this particular step isn't necessary to write, but it is good to have in the notes just because that's my thought process. That's what I'm doing. I would jump straight from this to what I'm going to have here. I would say, oh, okay, I got 2, 3, and 7. So 2 times 3 is 6. 6 times 7 is 42. Then for my x's, I have 1 times 2. So that's a total of 4 multiplied together. And then my y's, I have a y and a y and a y. So I have 3 y's multiplied together. And that's it for those. That's not too bad, right? It's pretty tolerable because those are just monomials. Now the next one I have set up to be very quick and very easy. It looks like it might not be, but it is. So on a problem like this, your first thought might be, hey, I'm learning about distribution, so I might want to distribute in, right? Not quite. On problems like this, you want to see if you can reduce the inside first to see if that is going to work out nicer for you. If you had distributed through, you might have treated these two as 2 separate terms, and that would be a mistake because these guys are multiplied together right now, which means those are going to end up as one term. So if I multiply that z onto both of them separately, I've just duplicated a variable, and that would blow up. So what I would do, I would look at this and I would remember that all my terms are separated by pluses and minuses. So there's a term, there's a term, and this whole thing, this multiplication over here is a term. So I need to multiply these guys together, right? So I'm going to multiply those together first. I have a 2y times 3y, that'll give me a 6y squared. And then I got these two guys, but these two are like terms, right? These two guys will go together pretty nicely. I have 14x minus 2x. 14 minus 2 is 12, so we have 12x. There's a plus between these, so there's still a plus between these. There's still that z out front. And now that we have the inside simplified, this is where we would want to distribute. That z is going to multiply onto that and onto that. The nice thing is neither of these has a z, so literally all we're going to do is 12x times z is, guess what? 12xz. 6y squared times z is 6y squared z. There we go. Not too bad. And they're not like terms. We can't put these two guys together, so we're done. Now, this next one is kind of similar because we see that multiplication is happening on the inside again. So again, we need to clean this up first. So I'm going to leave that negative 2w outside alone. That's just going to trail down until we're ready for it. We have w squared times y, w squared y, minus 3w squared times 7y. So we're going to have 3 times 7, 21. Then w squared and the y don't really go together too nicely, so they just kind of stack up. Oh, but these are like terms. How are they like terms? Because they have the exact same configuration of variables. This is 2 w's and a y. This is 2 w's and a y. So how would I combine these? Well, some people, I know that there would be a lot of people making this mistake where they would cross out the variables because they would see those crossing out. But no, what you think of is I have one of these right here. So you think of this as being a 1 w squared y. So 1 minus 21 is going to be negative 20 w squared y. So just negative 20 of whatever those variables are. We still have that negative 2w out front. Well, we now have one term times one term. So we multiply this term times this term. So negative 2 times a negative 20. Negative times a negative is a positive. 2 times 20, 40. And then a w onto w squared y. Well, we already had some w's already. So 1 w times another 2 w's. We're going to have w cubed. And that's y is still hanging out there with it. Okay. In the last of these examples, we have this monomial times these binomials. And again, doesn't matter if this guy's on this side or this guy, this side. We still have two terms multiplied onto one term, so the distribution is still going to happen. Now, which direction you do it in, it's kind of up to you. You could multiply these two together first and then these two. Personally, I would prefer left and then right, just to keep things more straight. So we have 5pq multiplied onto 3pq squared. So you look at the coefficients, 3 and 5, we have 15. Look at the p's, we have 1 times 1, so we have 2 of them now, so p squared. And then look at the q's, we have 2 q's multiplied onto 1 more q. So we have q cubed. Then we multiply this times that term. So we'll have 5 times a 2, that's 10. P squared times P would be P cubed. And then Q times Q is Q squared. And it doesn't matter how much you want to put these two things together. One is 2 P's, one is and 3 Q's. The other one has the opposite amounts. So these are not like terms that do not go together. We cannot do anything further with these guys. Yep. Pause for dramatic effect here. So that's all I have for review. Just that, not too bad, right? That was all the way we got up in multiplying polynomials right before we got to this, multiplying binomials. So these ones are a little bit trickier, but they're still just embracing the distributive property. So the idea with multiplying polynomials together is that everything has to multiply by everything else. You know, like if you had like, you know, you might be in like elementary school and you would be drawing lines to each group to figure out how many different groupings there could be. This is basically that idea, just with multiplication. So there's actually, for multiplying two binomials together, there's like a very common phrase that people use to keep it in mind, and it's called FOIL. And that's kind of how most people learn these. Now, I don't necessarily teach it exactly that way. It's just a good way to keep these ones in mind. So if you notice there, it says it stands for first, outer, inner, and last, which means the first thing you do is multiply both of the first terms inside those binomials together. Then you do the outer ones. Then you do the inner ones, and then you do the last ones. But notice that the first two, the first and outer, that's the A times C, and then the outer is the A times D. So what you're actually doing is you're taking that A and multiplying it by that whole other parentheses. And then if you look at the next group, the inner and the last, those ones you both multiply that B term through the other ones, right? So what you're really doing with multiplying polynomials together is you're taking the first term of the first group and multiplying it by the entire second group. And then once you're done with that, you move on to the next term in that first group and you multiply it by the whole second group. And you would just do this until you're done. And if you take that concept with you, that would scale up to anything. You could actually multiply, you know, a polynomial with 4 terms against another with 4 terms. You're not going to like to, it would take forever, but you could. So here's an example. So in this example, we have 3x plus 2 multiplying onto 4x minus 3. So using that FOIL method, which is first, outer, inner, and last, you multiply the first ones together. So you'd have the 3x times 4x. And then you would multiply the outer together. So you'd have 3x times negative 3. Then the inner together, 2 times 4x. And the last ones together, the 2 times the negative 3. So right there on that second to last line, that's what you would basically end up with when you're multiplying, right? Now, you're probably not going to write it that way. You're probably just going to end up jumping straight to this guy, because you would look at this and say, okay, what's 3x times 4x? Well, 3 times 4 is 12. X times X is X squared. So you would really just jump straight from the first line here to the last line. Then you do the outer, 3x times a negative 3. Well, that's a negative 9x. The inner was 2 times 4x. Well, that's an 8x. And the last was 2 times a negative 3. So you get minus 6 here. So once you're done with all that, you see if you have any like terms. Usually you will. Usually the ones in the middle will add together nicely, right? So in this one, we have the minus 9x and the 8x. So if you got 8, you subtract 9, you got negative 1. So that's where that minus x comes from in the middle there. And you have them all in a row, you're done. So it's a little funky, but we'll see if we can make it work. See if we can make it work. Don't worry, we have plenty of opportunities. I made, 6 problems. And I immediately started writing them wrong. First thing I did. So let's just look at that first one for now. We have x plus 3 times x plus 2. Remember while you're doing these, the word FOIL. First, outer, inner, last, right? So you multiply the first ones together. X times x, that's an x squared. Outer, so you take this first x and you multiply it by that guy. Notice what's happening, this one times both of those. So we have that x times 2, we get a plus 2x. Then we do inner, so it's this one times that one. 3 times x, we have 3x. And then last, 3 times 2, we have a 6. And again, you usually have like terms on problems like these, as long as, you know, they have the same variable. So those guys in the middle will add together. We have 2x plus 3x. That's going to give us a 5x. And the other ones stay the same. So we are good with that. That's multiplying binomials. You might get more complicated looking, but the concept won't be. Next one is a little bit more complicated looking. So we have x squared plus 2 multiplied onto x plus 4. Now, normally, when you're taking a class on multiplying binomials or something, usually your homework ends up being like 20 problems that look almost identical to this, and they get a little bit more complicated as you get further, right? So I figured, let's just jump into something a hair more complicated right away. What's the difference? Well, we have a square there, right? But the method is still exactly the same. You would still start with the first and multiply it by the first over here. X squared times x, x cubed. Then you would do the outer, x squared, bless you, x squared times 4, we have plus 4x squared. Then the inner, plus 2x. And the last. So 2 times that 4, we get an 8. Now what happened here? We don't have like terms. Well, that's what happens when you don't have the exact same set of variables on each one. Sometimes you get stuff a little bit more complicated. We end up with a polynomial with degree 3, right? It's a little bit bigger than before, but we have no like terms, so that's all we needed. A little bit more complicated, but the concept is exactly the same. Okay. Look at the third one. Is x plus 5 and x minus 5. Now, when you have something like this, where it's the same terms, but with a different sign in between, something interesting happens. And this is actually going to come up again in the very near future when I'm doing factoring later in the class, because there's actually a rule that deals with this. So let's see what happens. First, x times x, x squared. Outer, x times a negative 5, we get minus 5x. Inner, 5 times x, we get a plus 5x. And last, 5 times a minus 5, we get a negative 25. Well, look at our like terms. They cancel out. End up with x squared minus 25. This is actually, when we do the factoring, this is actually something special called the difference of squares. Why is it called a difference of squares? Because when you subtract two things, it's a difference, and both of these are perfect squares. That's literally it. It's named after what it is. It is the difference of two squares. Okay. Let's do another. Zoom in through this class. It must be squared. So the most common mistake I see on sections like these that students will do is that they would distribute that square through and say this is a squared plus b squared, which is not the case. You cannot just distribute a square through into a polynomial. It has to be like factors. You could square a factor, but you can't square a polynomial on its own without distribution. So what you end up doing is, well, what does this exponent mean? It means I have this thing multiplied by itself twice. Well, that's what we're going to do. We're going to expand it out a little bit. And there we go. So we would do the exact same thing. A times A, we have a squared, then the outer, a times b, we get plus ab, then the inner, b times a. Now you might be tempted to write that as ba. There's nothing wrong with that. It is still true, but I'm going to write it as ab in alphabetical order so I can more closely tell that I'm going to have like terms. Now, if I had written BA, they would still be like terms, but you might not see it right away. And then the last, b times b, b squared. Now, our like terms are hanging out in the middle. We have an AB and an AB. So if I add those together, well, I got one of them and one of them, so I have two of them. So I get a squared plus 2ab plus b squared. Now, one thing I will mention, I don't have slides for it. It didn't seem to be covered in the HSE stuff that I have, but this particular situation, this a plus b squared equals a squared plus 2ab plus b squared, This exact thing is actually a formula for a perfect square trinomial. And in most algebra classes, this is a formula that you end up having to memorize. Now, do you have to memorize it? Well, no. We just proved that we could do it anyway, right? But if I was sitting there doing a couple hundred of these things, knowing that it's just going to end up being this and being able to jump straight into it might be useful. So I just wanted to have that in everybody's notes so you can see that, hey, we kind of have covered it, but we also really didn't because I just kind of proved it. So you see something like this, instead of memorizing a new thing, just think, oh, write it twice and distribute. The easiest way I can go about that. Okay. Let's see what I have for number 5. I do not remember. Why did I do that? All right. So this one, a little different because we have more variables than usual. But again, we just have a binomial times a binomial. The method stays exactly the same, no matter how complicated these guys are going to look. If I got 2 things times 2 things, we still end up doing first, outer, inner, and last. Still do the FOIL. So again, first, we have 2x times 7x. 2 times 7 is 14. X times x is x squared. Outer, we have 2x times 2y. Well, 2 times 2 is 4. X times y is xy. So we have plus 4xy. Then multiply these guys together, the inner. We have 3y times 7x. Well, 3 times 7 is 21. And x times y would just be xy. And then if I do the last, I have 3y times a 2y. So 3y, 3 times 2 is 6. Y times y, y squared. Then you check to see if you have like terms, which we do. The 2 guys in the middle have the same variables. Now, if I had done the inner a little differently, the 3y times the 7x, I might have done it in the order that I just said those variables out loud. I might have written 21yx. They would still be like terms because they still have the same variables. But again, if I write them in alphabetical order, I don't have that problem crop up. So I have 4xy plus 21xy, so 4 and 21 is 25xy's plus that 6y squared. Nothing else I can do to that. Right. And I just have one more example for just the binomial multiplication. This one, I have a 2x plus 2 multiplied onto a 2x minus 2, and then an x plus y multiplied onto that. So we have three binomials. Now, I set this one up to the point where I know I'm going to end up with 2 binomials again. But if you ever find yourself in a situation where you have multiple polynomials to work together, you would just kind of pick a couple that you want to work with, multiply them together. Whatever else there is, it just trails down. and then you would bring another one. So right away, this one looks very similar to the one we did earlier, where it was the same stuff with a different sign in between. So I would say I want to multiply those two together first, right? Those are going to be the easiest to multiply together. So first, we'll have 4x squared outer 2x times -2, we have minus 4x inner 2 times 2x, we have a plus 4x. And last, we have 2 times the -2, which is minus 4. Now, how am I going to write this? Because I still had this guy, right? So technically, this is all happening in their own parentheses. These guys are joining together. And then this x plus y, it's just kind of hanging out, waiting for us to get to it. Well, now what? Well, see if we can clean that up, which we can, right? The middle terms cancel out again. We end up with 4x squared minus 4. And then we have our x plus y. Well, now it seems like a good time to actually bring that in, right? Now I have a binomial times a binomial again. So again, first, 4x squared times x, 4x cubed, outer, 4x squared times y, 4x squared y, inner, minus 4 times x, minus 4x, and last, minus 4 times y, minus 4y. Do I have any like terms? No. I have 3 x's, I have 2 x's and a y, I have an x, and I have a y. None of these go together nicely. We are done. And that's probably about as weird looking as any boiling problem you really have to do. Right? So are we feeling okay on binomials, or do we need to do a few more? We're going to assume the silence means we're good. Let's look at the next stuff, which is multiplying higher orders of polynomials. So this is where I'm just going to start looking at multiplication of things that aren't just monomials and binomials. How do you deal with trinomials? How do you deal with polynomials of the 4th degree? So on all of these, you end up, like I said, using the distributive property. You take the first term in the first polynomial and multiply it by each term in the second. Then the second term in the first polynomial by everything. Then the third in the first polynomial, etc., etc. That's really it. Just be careful about distribution. So I, of course, have a bunch of examples. By a bunch, I mean 4. 4 isn't really bad. Again, normally in an algebra class, you probably wouldn't get to this till the next lesson. So it's not honestly that bad. I don't know why they don't just teach all of this at once, because it fits together more nicely. So I have x plus 3 times this trinomial, x squared plus 2x plus 1. Now, this one doesn't fit the FOIL thing, but we still kind of follow that structure. We're still going to take this first guy here, and we're going to multiply it onto this one. So x times x, x squared, or x cubed. We have that, then it's not really an outer because this one has two more terms. You're going to keep taking this one and you're going to keep multiplying it onto that trinomial. So x times 2x, we get a 2x squared. And then we take that x and finally make it to the last one, x times 1 plus x. So all we've done is we've taken this x and distributed it through. Well, guess what we do now? We move on to the next term in that first, that 3. So we do the 3 times the first term there. We have plus 3x squared. Then we do that right there. That one times the middle, so 3 times 2x, we end up with 6x. And then we can do finally the 3 and the 1 plus 3. Now, if you've done this correctly, before we combine any like terms, we just had 2 terms multiplied onto 3 terms. What's 2 times 3? 6. 1, 2, 3, 4, 5, 6. We have 100% distributed everything to everything else. And you can actually check that idea with this stuff up here. Just looking at these 2, I had 2 things times 2 things. So I ended up with 1, 2, 3, 4. 2 times 2, we had 4 terms before cleaning it up. And that'll actually work out every time. If you take how many terms you have in one polynomial, multiply it by how many terms you have in the other one, that's how many terms you will get from the multiplication. Now, it doesn't have anything to do with how many you're going to have after simplifying, but that's an easy check to make sure that you didn't miss anything, didn't accidentally blow something up. It's just a good way to go. So how do I combine like terms on something like this? We have 6 terms. This one might not be as horrifying as you can imagine, but imagine having 9 of these. Imagine having 15 of these. How do we keep it straight? Well, what I've always done is I've always started with the highest degree term. So x cubed, right? And then I say, do I have any like terms? No. So I have my x cubed. And I'll usually just kind of underline it. I don't like to cross it out because I like to be able to go back and look at my work. But you can just cross it out to say, yeah, I'm done with this. But I'll usually underline. And then I might underline the next one. I did x cubed, how about x squareds? That's these guys. Plus 2 of them, plus 3 of them, so we have 5 of them. Okay, how about x's? X and 6x would give us 7x. And then we just have one term we haven't dealt with yet, that 3. And see, by doing it this way, I can see what I haven't taken into account yet. So again, it's just another way of keeping this straight, staying organized. Because you could very easily get disorganized with stuff like this. But that's all we needed. Right. Now I got a huge thing, but it's not bad. Just gonna copy it over here. Number 2, and it's a 2x multiplied onto 3x to the 4th plus 1/2 x cubed plus 4x squared plus 18x plus 3. So again, as weird as that might look like, with as many terms as it has, it's actually not bad. Because again, we're just going to use the distributive property. And we don't even have a polynomial here. We just have a monomial, right? We have one term multiplied onto these 5. So the distribution is literally just going to be that into each of them. 2x times 3x to the 4th, we have 6x to the 5th. 2x times 1/2 x cubed, well, 2 times a half, that's 1, right? And then x times x cubed, x to the 4th. I don't have to put the 1 because 1x to the 4th is the same as x to the 4th. Then the 2x onto the 4x squared. We have 8x cubed. Running out of room up top. 2x times the 18x. Get 36x squared. And then 2x times 3 plus 6x. We have no like terms. So even though this thing's nice and big and ugly, we got it done in one step. Not bad, right? It's really just all about the distributive property. Okay. Let's do number 3. Number 3 I did just to kind of have it a little bit weirder. So number 3 has an a plus 1 squared minus 9. What the heck do I do with that? Well, just like the earlier ones where we had 3 multiplied together and the one thing just had to trail out at the end. This is basically a term right now, right? Because we have a thing to a power, minus 9. So I can't do anything with this minus 9 until I clean this thing up. Okay, cool. I was about to ask. Okay. I was typing. I don't need to type. Okay. All right. So we have a plus 1 being squared minus 9. So since we have a binomial squared, we're going to have a plus 1 multiplied by a plus 1. I'm just going to have that minus 9 trailing off to the side. It's just going to go down until we can actually like bring it in. So again, we're going to multiply this guy through, just the same as the FOIL method. First, we have a squared. Outer, a times 1 is just a. Inner, 1 times a, again, another a. And last, 1 times 1. My goodness, it's a 1. But now, nothing's acting on those parentheses. So these guys can all be, you know, we got like terms here, but we also have like terms right here. So we have a squared plus 2 a's. And then 1 minus 9, we have minus 8 right here. Minus 8. Cool. Right. Now I got a huge one for no good reason other than the fact that I wanted to spend time on one. So if you didn't understand any of the other ones, this is the one to get down because it prizes the concepts. remember, it did say that if I multiplied the amount of terms in one against the amount of terms in another, it would show me how many I was going to have after multiplying them together. Well, I have 3 terms multiplied onto 3 terms now. That's going to end up with 9 terms after I'm done multiplying through, right? So it's going to be big. So I might not necessarily draw all my lines. I might just say, hey, I'm going to multiply this 2w squared into this. Now, again, we just take this one and we're going to multiply it by all of these, each one. Okay, so 2w squared times w cubed, we get 2w to the 5th, 2w squared times 3w squared, we get 6w to the 4th, then 2w squared times 6, we get 12w squared. Cool. There's 3 of them. Well, now we need to move on to the next one right here. We're going to take this one and we're going to multiply it by all of these. So 4w times w cubed. So we'll have 4w to the 4th. 4w times the 3w squared. 4 times 3 is 12. W times w squared, w cubed. 4w times that 6. We end up with 24w. Well, now we have the problem that I'm running out of space, right? Fear not, I'm just going to start a new line. Then we move on to the next one. In fact, the last one. That 3 is going to multiply onto all of these, which is a lot nicer to multiply because we don't have to worry about the variables. 3 times w cubed is 3w cubed. 3 times 3w squared is 9w squared. 3 times 6, 18. So I've now multiplied each thing in this one onto each thing in this one. That means we have covered all of our bases, but now we get to combine like terms. You can see how this could be weird. I've once done a, I think it was a differential equations problem where I ended up with like 3 rows on a whiteboard of things that had different amounts of X's and Y's. And that took me a really long time to put together. So again, I like to start off with my highest degree and say, okay, there's nothing else that it's going to combine with. So I have just that. Then I'll look at the next one, which is the 4th power. I got 1 here and I got 1 here. So 6w to the 4th plus 4w to the 4th is 10w to the 4th. Okay, now what about the third powers? Well, there's 1. And there's 1. So I have 12 of them plus 3 of them. I get 15 of them. And then squareds. Well, we got 1 that I haven't touched up here yet. And then 1 down here. So I have 12 of them plus 9 of them. That's 21 w squareds. What else do I have that I haven't touched? Only the things I haven't underlined, right? So I can immediately, my eyes just glaze over all of these. I see one thing and I see another thing. These aren't like terms. I have nothing that goes with them. So they're just going to take up the end. 24w plus 18. So I ended up with a total of 6 terms. Ugh, right? But it works. But it works. So again, it's all just about making sure that each thing in this first parentheses multiplies onto each thing into the second parentheses. As long as you keep that straight, you can do just about any of these. You could do 4 times 4. I just don't recommend it. That would take a while. But it could be done. I'm not going to do one right now. That sounds terrible. It's not going to. Okay. Do you have any questions on polynomial multiplication? Polynomials going once. Polynomials going twice. Okay. So now we have factoring. Now factoring is, honestly, it's literally what we just did, but backwards. It is taking a large expression or polynomial and pulling things out of them instead of distributing things into them. So it transforms expressions into multiplication. So like I say here, it's like splitting an expression into a multiplication of simpler expressions, which is, again, pretty much just breaking things down, right? So best way we could do this is think of the greatest common factor. When we're just doing the really basic ones, like for example, here we have factoring 6x squared and 18x. So you would look at this and say, well, what's the biggest thing that could come out of both? Well, between 6 and 18, both would have a 6 in common, right? And between x squared and x, they would both have an x in common. So we can say that the greatest common factor between those two is 6x. So what you end up doing is you factor it out. So you're kind of undoing multiplication. So you're kind of dividing it out. So you would write the 6x and then start a parentheses, and for the parentheses, what you would do is you would say what you'd have left if you took that 6x out of each term. So if I divided off the 6x from the 6x squared, I would have an x left. If I divided 6x off of the 18x, well, the x's are taken care of, but 6 out of 18, that leaves me 3, right? So you end up just pulling out the greatest common factor and making a parentheses of what you have left. Now, there's not much more to that than what we have here. So that's why I got some examples right off the bat. They are noticeably worse and worse as it goes. I regret nothing. Honestly, just trying to get through the next couple of slides so I can cover something else that I didn't prepare. Really want to cover. Because if you guys are unaware, Thursday is the last class. The next class that we're going to have for math is going to be starting up in January. It's going to be quite the gap. Now, during that time, I don't care if you are still my students or not. If you have questions on any of this stuff, shoot me an email. I don't care if you're working stuff on your own. I don't care if you found something on the internet somewhere. Just shoot me an email. I will help you. Unless I'm at work, then I'll help you later. You know it. Just work on the first 3 and not the 4th. I don't know what's going on. So again, on each of these examples, we're only really worried about the greatest common factor. And if you haven't done that in a while, or you haven't done that in general, I don't really know. But all you would do is you would look at the coefficients first, and then the variables, and say, what's the biggest thing they would have in common? What's the biggest number that I would be able to divide off evenly from both? Now, between 2 and 3, nothing goes into those, right? Like there's nothing I can divide equally between 2 and a 3. So we have nothing in common between those, but the variables, we have an x squared and an x. Now between those, they have an x in common, right? So we know that that's our greatest common factor is the x. So we're going to start that off, and then we're going to start our parentheses. In the parentheses, we're going to say, hey, what do I have if I take an x out of each of these terms? Well, if I take an x off of a 2x squared, I would have a 2x. And if I took an x off of this 3x, I would have a 3. That's it. That is what we do. That is factoring. This actually ends up having a lot of different applications. But this is the simplest form of factoring you might run across. Now, of course, I didn't want it to be that simple, so I made a bunch of messy problems. So let's look at the second one. Between the coefficients, we have a 14 and a 7. Okay. Well, between 14 and 7, I know that 7 goes into each of those. And then we have 5y's and 4y's. Well, they each have at least 4y's in common, right? 7y to the 4th. So that's going to be our greatest common factor. And we start our parentheses. And we say, hey, what do I have left? If I take a 7 out of a 14, what do I have? You divide it, so it'd be a 2. But what about the variables? If I take 4y's away from these 5y's, I have 1 left over. Right? Well, what about this term over here? That whole thing is this common denominator, or common factor. Is that, does it go away? Do I close my parentheses? No, because, yeah, exactly. Because you need something to be here, or if I distributed it back out to get this. So if I divided this thing by itself, well, what do you get when you divide something by itself? 1.
Trick question, right?
Well, that's a common mistake I see is people saying that they're taking that whole thing out, so it just poops. Because a lot of people cancel things and think zeros, but what they should be doing is when you're canceling things like that, you think ones. This divided by itself, 1. Not 0. And you want to be able to make sure that if I was to distribute this back through, I would end up with the same thing. Which, yes, 7 times 2 would be 14, y to the 4th times y would be y to the 5th. And then 7y to the 4th times this minus 1 would be minus 7y to the 4th. So you can distribute it back through if you need to check. So, number 3, looking at all of our coefficients, we have a 3, we have an 18, we have a 6, and we have a 2. We might look at that and say, hey, 3 goes into both of those, and 2 goes into both of those. But our problem here is that we're trying to find the greatest common factor overall. And we have that same problem with the 2 and the 3 that we did up here. So even though that 3 would go into here, here, and here, and then 2 would go into here, here, and here, nothing goes into all 4 of them at once. So there's no common factor between the coefficients. Now with the variables, well, there are. And in fact, what happened? Look what we have. We have like terms. Now, if you end up with a problem that has like terms, I recommend combining them before you start playing around with this, right? We don't really need two separate terms with these a squareds on them, right? I don't even remember if I did that on purpose. I'm pretty sure I did. But again, I'm just going to go ahead and combine this one with that guy. So I'm going to rewrite the 18a to the fourth minus 6a cubed. And I'm going to combine these two like terms. So we have 3a squareds plus 2a squares. So we have 5a squares total. Well, cool. We got rid of one term already, right? Now, again, we have a 5. There's no common factor between the coefficients, but the variables, well, they each at least have that a squared. So we could pull out that a squared. And then you would have, well, 2 less a's on everything, right? 18a squared minus 6a plus 5. We're just taking 2 a's away from each of these. Okay. Now just one left. We have x plus x cubed y plus xz plus x squared w. Gee, what's our common term here? The only thing they all have in common is an x. So if I pull an x out of everything, what do I have left here? If I divide this x by this x, get a 1.
Yeah.
Plus, if I take 1x away from everything else, if I have x cubed here, it's going to go down to x squared y. My x's are awful looking. If I pull an x out of this xz, I just have a z. And if I pull an x out of x squared, you have x with that w that's hanging out there. Now, you don't have any like terms, you don't have anything else that you could do. So despite the fact that this problem looks kind of funky and complicated, if all I'm doing is factoring out a greatest common factor, we are done. There is nothing I can do to that thing. So that's not too bad, right? Factoring out a greatest common factor, it just boils down to recognizing what all the terms have in common, right? Not too bad. Well, let's make it worse. Remember that difference of squares thing I mentioned earlier when we were doing the division, the binomials with binomial? Well, here's where it comes back. This is where we're going to be able to go backwards. And this does involve remembering a formula. So a difference of squares is a binomial that has perfect square terms subtracted from each other. For example, in this case, 4x squared minus 25y squared. Everything in there is a perfect square, right? So in order to factor them, you have to identify what's being squared and then factor according to the formula there. So I actually think I would rather have that written the other way around. Not that it really matters. Doesn't really matter, but that's the general structure you're going to have. And a squared minus b squared is equal to a plus b and a minus b. So if you see two perfect squares subtracted, you can immediately jump to two separate binomials. Now, one thing I thought about having a slide on that I didn't really think deserved having its own is that when you have a binomial and you're told to factor it, there's really not a whole lot you could do with it. you can pull out a greatest common factor, and if there is one, you would always do that first. And then you check to see if there's a difference of squares. Well, if there is, then you do it. If there isn't, then you don't do it. That's really it. The only other thing there's rules for is difference in sums of cubes, which I am not going to throw at you, because those are uglier and you use them. I think I had to use it like 3 times when I was getting my degree. That was it. So not really too often. Doesn't come up. Every time you use it, you tend to look for the formula. Like I've said before, as long as you understand how to work with a formula, you're gonna be okay. So 4x squared minus 25y squared, you identify what's being squared. Now, when people are starting off, I usually recommend writing it out like I have in the middle here. So before you understand everything fully, before it's clicking, you know, having that in-between step can kind of help out a lot. So you identify what's being squared, and then you just split 2 parentheses and say, hey, it's that first one on the first of both of them. It's the second one on the last of both of them. And then you put a plus in one and a minus in the other. Which one's which? I don't care. It doesn't even matter. That. And then like I have down there, when factoring anything at all, look to see if there's a greatest common factor first. Because sometimes there is, and sometimes that'll make your life easier. And also, if you're told to factor something fully and you don't, well, you've got it wrong. Look at all them examples. Let's do a bunch of these. Oh man, I've made it to the part of my bless you. It's the part of my notebook where it's lined instead of dotted. It's like my personal, hey, you haven't actually scanned and erased stuff in a while. Of course, I'm just copying things down. We're gonna have enough time to randomly cover. So another good thing to do is when you're learning something new and you have a formula, either write it on every single problem or write it up top so you can reference it. Even if you have it written somewhere, the act of writing it down. Why is my screen going super fast? I don't think my screen's going super fast. My screen going super fast to anybody else? Okay. Because your internet was angry at. Such is life. Such is life. Yeah, but whenever I'm learning something new and I have to use a formula, or honestly, if I just have to use a formula over and over again, I will just write it on that paper to reference it, just because it's going to be really easy for me to glance up and see it. And me writing things down is going to cement it better in my mind. Okay. So again, like I said, there's that middle step that you can do until you're feeling comfortable with this stuff, where you could say, hey, what's that a square of? Well, 25 is the square of 5. W squared is the square of W. And then what's that a square of? Well, 2. So you can have this little in-between step. that makes you more comfortable. You don't have to. So, according to the formula, when I have a perfect squared minus a perfect squared, what the first one squared of goes on the fronts. What the last one squared of goes on the lasts. And then a plus and a minus. And since they're the same terms, it doesn't matter which one has a plus and which one has a minus. So I have a 5W on the front of both of them. And then a 2 on the back of both of them. Put a plus in one, put a minus in the other, and we have successfully factored. Cool. Not too bad, right? It's actually pretty decent. Now, number 2. Until I did this like 100 times, it took me forever to recognize that 1 was the square of itself. That would always trip me up. When I was doing these problems, I would always be like, there's nothing I could do. That's just a freaking 1. Well, 1 squared is 1. So this is still a difference of squares because it is its own perfect square. So it's kind of cheap, but it works. Okay. So let's say I didn't want to do that little in between step. Let's jump straight to the answer. I'm so confident in that, I'm going to put a box around it right now. Look at that. Look at that. Okay, well, what's 100y squared the perfect square of? Well, 100 is the square of 10, and y squared is the square of y. So 10y, right? So you put a 10y here and a 10y here. And then you say, okay, what's 1 the square of? 1. Okay. Put different signs between them, and you're done. Not bad. It's a really easy formula to remember if you, honestly, if you do it like 20 times. You know, doing 1 or 2 tonight, and then thinking, yeah, I got this when I take that test in a month or something. I think I cut it. You gotta do a bunch of them. You gotta practice till that sticks in your brain. All right, number 3. We have 9n squared minus 36m squared. Okay, same idea. What's the 9n squared a square of? Oh, 3 and an n, right? 3n, 3n. Cool. All right, well, what's the 36m squared the square of? Well, 6 and an m, right? 6m and 6m. You put the plus and the minus together, and are we done? Well, here's the thing. We are not. We are not. Because if you look at both of these sets of parentheses, there's a greatest common factor in both of them, right? I can pull a 3 out of both. Now, when that happens, you can fix it. But it just means that there was a greatest common factor at the beginning that we did not take into account. So like I said, you always have to look for the greatest common factor first, because you want to be done here. But if you turn that in and say it's fully factored, you are wrong. So there is a way to fix this. This is where I usually see somebody frantically erase. I'm not going to erase this. You can fix this. You could say, well, just do exactly what we did earlier with the factoring of like a binomial, like pull out a greatest common factor here. I could pull out a 3. Just because I've already done this stuff doesn't mean I can't. I could still pull out that 3 and have an n plus 2m right there. Okay, cool. Well, what about this one? Well, actually, I'm going to go ahead and do the same thing. Now, since it's between a bunch of stuff in parentheses, I'm going to put that 3 in parentheses, but it is just a greatest common factor of that. So I have 3 coming out of both of those, I'm gonna have an n minus 2m. Oh, okay, all right, so see, that's where that would have been. So I have 2 3s, I can multiply those together and have a 9, and then the n plus 2m, and the n minus 2m. That is what we want. There's no more greatest common factors. Now, what's the correct way to have done this? Correct way would have been to start off there and say, hey, do I have a common factor? Yes, I can pull out a 9. And you would have had n squared minus 4m squared. And that's the difference of squares we would have used. You would have said, hey, that is the square of n. That's the square of 2m. And you just put different signs in between them. So you can see it's a little messy when you got to go back and fix stuff. But sometimes it's worth it, sometimes it's not. Use your best judgment. But like I always tell people, if what you've done is valid math, you're not wrong. You just might have gone a better direction to start. That doesn't mean you can't course correct it and fix it. You can fix it most of the time. And sometimes you're like, oh God, I see what I could have done. This would have been so much easier. And you scrap the whole thing. And that's fine. That's a good way to go to. Just use your best judgment. Now, speaking of best judgment, I have the same problem, a plus in between. What do I do? I have this question here for one reason and one reason only. There is no rule for the sum of squares. There is no rule for that. I will see people try to factor things like this all day. You can't. There isn't some magical rule for it. If there is no common term, you're done. So literally all I could do with this guy is pull out that 9 and out of n squared plus 4m squared. And that is fully factored. You cannot go any further. There is no rule for a sum of squares. We have a difference of squares. Having a plus there means it's a sum. There isn't one. There is no factor rule for that. In fact, the closest you get is that example I used earlier where I said, hey, this is actually the definition of a perfect square trinomial. That and this are usually taught in the same class at the same time. It's factoring perfect square trinomials. I'm not going to do that because I could do it the same way with regular trinomials. Why teach you 2 ways when 1 way will work fine for now? But that's the case then. Now,
Just because of that plus sign.
just because of the plus, there is no factoring rule for that. Man, I should have brought a water bottle. I got an hour to go. All right. So, number 5. Number 5 is back to business as usual. Well, now we're on the lookout. There are no greatest common factors, right? So we can just jump straight to our difference of squares. 4x squared breaks down to 2x and 2x. That 9 is going to break down to a 3 and a 3. And then you put a plus and a minus in between, whichever one you feel like, and you're done. Now, number 6 might look familiar. That was one of the Euling distributing binomials examples. And I always liked having these as examples because they terrify everyone. This is as complicated looking as a difference of squares could look. This is a difference of squares. It is already there. Because this thing is just a thing, right? It's a thing squared minus a 3 squared, right? Well, this is where you all hate me. You're like, what the hell just happened? What's that first guy being the square of? The square of a plus 1, right? Can I technically do this? Yes. Yes, I can. I can absolutely get away with this. What's that last guy the square of? 3. Then you'd have a plus and a minus in between, right? Well, wait a second. Those both have like terms, right? A plus 1 plus 3, that's a plus 4. A plus 1 minus 3, that's a minus 2. That's as simple as you can get it. But one thing I do want to show you guys, what the hell do I get if I distribute that out? Because we started with this, but what would I get? What if I FOILed this guy out? A times a squared, a times -2, so outer, minus 2a, inner, 4 times a, plus 4a, last, 4 times -2, -8. Combine like terms, a squared plus 2a minus 8. A squared plus 2a minus 8. So it is the same thing. Just now we know this thing would actually factor to these two separate binomials. And that's actually the next section, is factoring trinomials. We would be able to actually go straight from this to that. Isn't that fun? So much fun. Those are great examples. So again, for those of you who might be dizzy now, the a plus 1 was the first thing being squared. So we put it in the front. And the 3 was the second thing being squared. So we put it in the back, put a plus and a minus, and then combined like terms. So it still worked out nice. And we can use our earlier problem as a check. This is why I like these examples. Okay. So I have one more concept on factoring trinomials, or on factoring, and that's trinomials. After this, I should hopefully have enough time to cover one more thing. Since Thursday is our last class, I would like to have a class for solving quadratic functions, because those are a little funkier, those are a little more difficult. But what I'd like to do tonight is do some of these systems of equations. That's basic enough to the point where I'm pretty sure I can teach that to you guys at the end of this class. So this one will go to 8:30. Mark my words. Unless I fall over and die from dehydration, which is actually a possibility. I think the last time I actually drank water was like 2 weeks ago. Yeah, no, I don't know how I'm alive. I really don't. No idea. Okay, so factoring trinomials. Little funkier, but it kind of works out similar to the difference of squares, where you're just finding what things are being squared for the first one, but the last one you end up finding not necessarily what's squared, but what's multiplied. So factoring trinomials is writing an expression as the product of two or more binomials and is written as x plus m times x plus n. So x in a number and x in a number, kind of like all the difference of squares, right? So generally it involves trinomials with degree 2. I say generally because it technically can work with higher degree things. It's just very specific, and I'm not going to show you any of those. But this is going to be the general example for every factoring trinomial ever. So we're going to use the standard form of trinomial for the use of this explanation. Ax squared plus bx plus c. In order to find factors of c, or in order to factor trinomials, we need to find factors of c that add to b. I should have on here, this method only works when a equals 1. So this only works if you just have an x squared on the front, or a y squared, or a w squared. It's not going to work if you have a 2x squared. It's not going to work if you have a 7x squared. You might be able to pull out a greatest common factor and then work it after that. But if that a is any more complicated, if there is a number on that squared term, you have to jump to another method. Don't believe that method is on the HSE or the GED, so I don't have that covered. If you need it, it is called the AC method, and you do something called factoring by grouping, which I would love to teach you guys, but I totally don't have enough time. But I actually really like doing that. It's kind of enjoyable. I don't know why. Because I'm a freaking nerd, that's why. All right. So our first example is going to be x squared plus 6x plus 9. Now this one's actually, interestingly enough, an example of a perfect square trinomial, which is what I mentioned earlier in that one example in the review. So the easy way to deal with these is you look at the last term and you say, what factors of this can add up to the middle term? Well, if I have a 9, my brain immediately jumps to 3 and 3, right? And 3 and 3 would definitely add to that 6 in the middle. Now, it might not be the first thing that comes to mind. It might be others. So sometimes you end up listing a bunch of factors. That's fine. So when you set up your separate binomials, the first terms on each of the binomials are just an x or whatever variable it is you're working with, because those first terms multiplied together will end up being that first term in general. So that x times x is going to end up being x squared, right? If I FOILed it back out, that's what I get. So you would look at this and say, all right, well, the two factors that add to that middle term, those are going to be the pieces that you have on the other parts of your binomial. Now, in this case, we do end up with x plus 3 times x plus 3. So it would actually be x plus 3 squared. You would want to, since you have 2 of it, you would want to leave it as that. But this will make a little bit more sense when we're getting into the actual examples. Now, this particular slide is just honestly take a picture, take a screenshot, you know, go back to this. I'm probably not going to have it on the screen long enough to, you know, write down the whole thing. So check out the notes later. But the signs are important. The signs are very important because if I'm looking for 2 things that multiply out to the last term, well, if that's a positive versus that being a negative, that's going to make a difference. If 2 things multiply out to a negative, well, that means one of those numbers is a negative number, right? Whereas if 2 things multiply out to a positive, that means either they're both positive or they're both negative. So that's the main thing. Now, if you look at that first bullet point, they're all pluses, so all your signs are going to be plus. Nice. Now the second one has a minus on it. And if you have a minus at the end, that means that you're going to have one of your factors with a plus and one of them with a minus. Now, which one's going to have which? Well, if they're both adding up to a positive number, that means your bigger factor is going to have the plus on it, right? Whereas if we look at the third bullet point, same sort of thing happens. We have a minus on the end, but there's a minus in the middle. Well, that means that your larger factor had a negative on it. So those kind of fall together pretty nicely, actually. And then if you look at that last option, if the last one's a plus, but you have a minus in the middle, well, in order to get a plus at the end, think about the fact that each of these are going to be binomials that would boil back together to be a trinomial. So the last two terms multiply out to that number. If both of them multiply out to a positive number, then they're either both positive or both negative. So if I have a minus in the middle, they're both negative. Ooh, look at all them examples. Look at them. Okay. I'm going to write a few of these down. There's going to be very little room in between them because there really isn't a whole lot of work to be done. Now, I only have one example where it's actually going to matter. But like I said earlier, anytime you're doing any factoring, you always look for a greatest common factor first. Now, if you look at these examples, you can probably guess which one of those is going to have a greatest common factor. Number 6, because it has a number out front, right? We would not be able to factor that with that 2 out front with the skills that we have right now. You know they're not going to be bad when I write all of them crammed up right next to each other like this, right? That's the nice thing. It's not going to be bad. Every single one of these, well, we have a trinomial. It's going to split to a binomial times a binomial. Our first term's an x squared, so honestly, all of these have x squareds. So we're just going to have an x on the front of each one, right? So the question is, what are factors of 8 that add up to 6? Now, one thing that's useful for more complicated problems is to make like a little chart of the factors. Now, I intentionally didn't make any particularly difficult problems on this one, just because I want you guys to get the concept. But we can see that 2 and 4 would go together quite nicely to add to 6, but multiply to 8. Now, all of these signs are plus, so this is going to be +2 and +4. If you're ever not sure, you can absolutely just boil it back out and see if you end up with the original problem. Okay. Same thing. But this one has minuses all over the place. Now, for this particular example, I want to show you guys something I do. I've never seen any other teacher do it, but the second I started teaching it this way, it seemed to really work out when I was tutoring. I was at the Skills Center for tutoring. So a lot of people rolled with this. I'm not just going to take the 8 and make a little chart over here. I'm going to take the -8 and make the chart, because that's going to remind me that one of my signs needs to be negative. So I'm going to have the same things multiply out, but I'm not looking at 1 plus 8. I'd be looking at a -1 plus 8 or a 1 plus a -8, because one of these has to be negative. So you look at this and say, which of these has a difference of 2 instead of add to 2? Well, 2 and 4, right? 2 and 4 have a difference of 2. So you would put the 2 and the 4, but then you have to make sure that your signs are very carefully put there, because we know that only one of these is going to be negative. So if I'm going for a -2, I want a -4. 2 with a -4 would give me a -2, right? So that minus is going to be on that. So the plus would be here. Now, again, if I was to FOIL this guy out, the outer and the inner would give me that middle term. The outer would be -4x. The inner would be plus 2x. -4x plus 2x, that -2x right there. And then you multiply these guys together for the last, you get that -8. So you know we're good. Okay. Now the next one, x squared plus 4x plus 4. You probably can look at that and say there's going to be a bunch of 2's all over the place. I'm breaking things down. I know 4 is a perfect square of 2. What else am I going to have? 2? It's 2. I mean, we could have had 1 and 5, but it's totally going to be 2's. Factors of 4 that add to 4. 2. And they're both plus because they add to that positive 4. Whereas with this next one, they have to multiply out to that positive 4, but they both have to add to a -4, which means in this case, it's going to be -2 and -2. This one has to be that way, because the -2 times the -2 would give us a positive 4. The -2x plus the -2x will give us a -4x. Yeah. Oh, and for the record, I totally had one more step on both of those. This should be an x plus 2 squared. This should be an x minus 2 squared. Oops, whatever. I'm not going out of my way to fix that too much. Okay. X squared plus 3x plus 10. Well, factors of 10. 1 and 10, 2 and 5. And you would look at that 2 and 5 and say, hey, yeah, if one of those was negative, then I'd be able to get to that 3. Ah, but we have a plus. They have to add to that. Ah, so how the heck would I do this? Well, you wouldn't. What ends up happening is nothing. This one just happens to not factor. It might look like it would, but this one is prime. Prime polynomial, which means that you can't factor it any further. Now, as an example, just drop it over here. If I had an x squared minus 3x, it's not that sign, that's my problem. If I had an x squared plus 3x minus 10, well, if I had that minus 10, then that 2 and the 5 would actually work out because I could do a -2 and a +5. So I would be able to do that in that case. But our problem was that sign. That sign wouldn't let us get to a 3 in any way, shape, or form. This sign does, because it gives us the option of a negative. Okay. You know what I just realized? I just realized I actually planned for that explanation, because if I look at the next number and say, hey, there's a common factor, what do I get? I get the fact that I didn't need to do that as an example, because I forgot that I had it snuck into this problem. You know, because whatever. I wrote this a week and a half ago, guys. Don't judge me. All right. So this one still factors to x minus 2 and x plus 5. But there was a common factor of 2. See, I did a little bit more on that one. See? Yeah. There's a 2. Yeah. All right. So number 7, our last one, we have x squared minus 2x plus 1. What are factors of 1 that add to a -2? Well, what goes into 1? 1 and 1 and 1 and 1 and 1. Only ones would work, right? Can I get these to multiply to a positive 1 but add to a -2? Yes. Both of these signs would have to be the same to get a plus right here. But to get a minus right here, they both have to be negatives. This guy would be x minus 1 squared, because we have that one term twice. Okay? Now, this is where it gets creative, because I don't have I think I covered systems of equations once. Let's find it. This is the first time I taught. I jumped straight to it. All right. We're going to the first class I ever taught, because I did in fact write something for systems of equations. Okay, so you tell I had a different style at the time. All right. So systems of equations. Systems of equations. So a system of linear equations consists of 2 or more linear equations made up of 2 or more variables, such that all equations in the system are considered simultaneously. Why did I not write this in a way that is easily understood? I don't know. This was the first class I actually taught. I just kind of rolled with it. So a system of equations is literally, okay. So if I have an equation and I have an x, I could solve for that x. If I have an equation and I have a y, I could solve for that y. But if I have an equation and I have an x and a y, I can't solve for either. Both of them don't have an exact number, because it's relating a y to an x, right? Every line, every straight line is relating an x to a y. Blah, 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 functions, domains, ranges. I want to write on the board. I know that I don't have a good, like, it's shared to my webcam, but I hate how it's
Can't see it.
Yeah, you can't really see it all that well. That's why I do the notebook. Plus, it's nicer to be able to it's nice to be able to actually scan. Okay. Let's just look at this graph and ignore the crap on the left for now. So every line, take that yellow line, is relating an X value to a Y value, right? So every point along that line would make whatever equation of that true with an X and a Y. Now, if you had two lines would cross each other as long as they're not parallel. Yeah, if you don't do it, I will.
That was getting too out.
Loud as shit over there. All right. Thank you. So if you have two lines that cross somewhere, that means that there is one point where X and Y are the exact same on both lines. So what you do is you basically call that point the solution to the system of equations. If you are taking both of those equations and solving them together, you're treating the variables the same. So each X is like each X on each equation is the same X and each Y is the same Y. There's only one point where that happens, and that's where the lines cross. So that means that the solution to a system of equations is just the point where they cross. Now, I'm not going to go over examples on this. I do remember this funky meme. I'm not going to go over examples for this because honestly, using this method just gets you to understand, hey, the solution to a system of equations is where the lines cross. However, unless they're really, really nice equations that cross at perfect points, and you have really good graphs, which I don't, then this isn't very useful. If you are using like an online graphing calculator or something where you can put both lines and zoom in and say, hey, yeah, that's it. Cool, that's fine. But this is not the best way of doing this. So there's actually a couple of different methods for solving systems of equations. Do I really? Damn, I was bad at this. Okay, well, at least I have something to work off of, right?
Yep.
So, all right. So I personally, I hate how I have this written necessarily because there's no explanation. But the elimination method is one of the two methods that you can do on paper to solve systems of equations. There's elimination and there's substitution. Now, elimination is often called the addition method. Now, this ends up doing stuff that you have not seen happen in math up to this point. What you end up doing is you end up adding and subtracting the entire equations together. So for the elimination method, now you can call it the addition method, you can call it the elimination method. It's called both because the idea is that you're going to add the two equations together and that will eliminate one of your variables. You end up setting the equations so the variables line up. You modify those equations so that both equations have the same coefficient in front of their variables, one positive and one negative. And then you add them together and that eliminates that variable. So then you have an equation with one variable. You now solve for that variable and then you back substitute it to find the other one. So the modifying equations things is the tricky bit. Or one of the tricky bits, I guess I should say. So think about how you can multiply or divide both sides of an equation. This is an extension of that, but we're going to work, we're not trying to simplify a single equation, we're trying to get it into a point where we have the same coefficient on one of our variables. And one equation, we have the same coefficient on x. We get the other one to have that coefficient on x, and then we can add them together and they poop. And then you would have one equation with a bunch of y's. So it's tricky, but you can safely multiply any equation by a constant. And take my word for it, you can add or subtract an equation onto another equation. And as long as it's in the same system of equations, it is still functional. It still works. Okay? Huh? Yeah, they're loud as shit over.
I don't know what the hell's going on. No, it's an English class. But holy crap.
So, all right, I'm going to bounce around these examples. What I'm going to do is I am going to write down number 4 for now. I'm just going to put EX on each example because it's not going to be in the usual slideshow. And there's also some notation that I wasn't able to replicate on the slides at the time. So what is missing from all of the equations or all of the systems is that a system of equations normally has this guy on the side of it, a little curly brace thingy. And that is just to tell you, hey, this is a system. This x and this x, this y and this y are to be treated as the same variable. Now, the tricky bit here is solving them together. And that's why I wanted to work with this one to start. I'm just rewriting it over here because this is going to be where I do my first step. Okay. So if I look at these, and I know that my goal here for now is to get it to the point where either my x's or my y's, I don't care which, either my x's or my y's line up nicely to the point where I have the same number in front of either one with a plus or a minus on each. And that's exactly the situation I have here. I want to set it up so if I made these add together, they would disappear, right? Because y minus y is gone, right? So what you end up doing is you end up adding these equations together. And you make another equation. And this equation is going to be valid only for this system. Okay? So you add these together, you end up with 5x. The y's disappear. And over here we have 5. Okay. Well, that was weird. But I now have a line with a variable, right? So I can solve and get x equals 1. Now, what that tells me is that where these two lines cross each other is when x is 1. So now we got to figure out the y. Now, what we've just solved is that at the point x equals 1, the y value and the x value are the same on both equations. That's where they cross. So we've got to figure out what the y is, and it doesn't actually matter which of these I plug that 1 into. Because if I plug a 1 into here, or I plug into a 1 into here, and I solve for y, both of them are going to give me the same number. Because again, that is where these two lines cross each other. So that point is the same on both of those lines. So we have our x, we need our y. So you pick one of these that we're going to solve for y. I'm going to pick this top one because it has a positive y, and I don't want to deal with that. So I'm going to have 3 times, well, x is 1. I'm going to write x equals 1 above this, just so I can remember that this is where I'm substituting that in. So I'm just plugging a 1 in for x here. 3 times 1 plus y is equal to 5. Okay, so that's 3 plus y equals 5. If I subtract 3 from both sides, I get y is equal to 2. So I have an x, I have a y. So my solution is an ordered pair 1, 2, because if you remember, points on a graph are in the form x, y. So that is the solution to this system of equations. That is the point where these two lines cross each other. Isn't that fun? Yeah, it's weird, right?
Yeah, you throw me off.
Yeah.
Yeah.
All right, so let's do something hair trickier. Let's see this number 3. 2x minus y is equal to 4, and 6x minus 3y is equal to 12. Yeah. Now, one thing I could say is that I could notice that all of this has a common term of 3. So I could actually divide both sides on that equation by 3 and simplify it a little bit. You know what, this was a terrible example because I realized that these are the same lines. Actually, no, it's a good example because that only happens in this case. So, all right. We can tell right away that nothing lines up perfectly. So what you want to do is right away decide which variable you're going to try to eliminate. You're either going to eliminate x or you're going to eliminate y. We did y last time, kind of worked out for us. Let's do it again. I'm going to write that I'm eliminating y. Why am I doing this? Because I've seen people dance themselves in circles while doing these. So we're eliminating y. I mean, all right, whatever. Okay. So if I eliminate y, well, I can't really get this 3 down to a 1, but I could probably multiply this line by something to get it to a 3, right? So what I'm going to do is I'm going to multiply this line times a -3, because I want this number right here to be a +3. So you multiply the -3 through by this entire line, -3 times 2x minus 6x, -3 times -y plus 3y, -3 times 4, -12. Now this is honestly is a terrible second example because I did not get to plan this ahead. Normally, you would be able to add these together, have something with x and something with y, or something with x, the y would cancel, and you'd be able to solve for x and do exactly what we did in the last one and plug it in to find y. But what happens on this one? Everything cancels. Everything cancels. Now, something unique happens in this case. Now, what ends up happening is these actually ended up being the graph of the same line. If I pulled out that 3 right here on that second one, I would have had 2x minus y equals 4. This would have been the same line. But you're still treating them as if they're separate lines because they're separate things in the system. So the question is, where are X and Y the same on these two lines? Everywhere, right? Because we ended up solving this and dropping down, we got 0 equals 0. If you get a true statement, then that means that you can say infinite solutions. Infinite solutions. Now, the reason for that is because every single point on either of those lines is the same point on the other one. So the solution to all of these is every single point along that line. That one was a terrible second example. Let's after. You know what? I can roll this into. Yeah, okay. I'm probably going to just do some elimination, and then I'll start off Thursday with some substitution. I should have enough time for both of them. That'll work. Okay, so yeah, if I go for 3x plus 2y is 19, and x plus y is 8. And I had to solve those as a system. We're going to do the same thing. It's going to be just as confusing. There is a video on it on essentialed.com. Please watch it. So if I needed to eliminate one of these variables, I either need to get both of them up to 3 or both of them up to 2. Doesn't matter which, but I need to get, you know, something to line up nicely. So you pick one of the variables we're going to do. I'm going to eliminate x because we've done y twice. I'm going to eliminate x. It's the same amount of difficulty on both of them, this one. So if I was going to eliminate x, I would need this guy to be a minus 3x, right? Because I need to be able to add that to something that would cancel out. So I'm going to multiply this through by a negative 3. I get a minus 3x minus 3y equals minus 24. So you just multiply that negative 3 all the way through. And then we're going to leave that first one alone. Let's do. Now, one thing, I don't know which, I'm sure one of my examples does it, but I'm pretty sure I don't have the option right now. But one thing I do want to cover is if you get a false statement, if you work this out and you get like 2 equals 1 or something like that, then you would have no solution. This is just as an example, but that happens when you have parallel lines. Because if the solutions to all of these are where they cross, if they never cross, there is no solution. And you end up stumbling onto that if you get something where all the variables cancel out, you get some weird one number is equal to something that it doesn't equal. So you get a false statement like 2 equals 1, 0 equals 1, you get something small like that. It happens. Most of the time the lines cross, you get a situation like this. These guys combine, the x's eliminate. 2y minus 3y is negative y. 19 minus 24 is a negative 5. You divide both sides by a negative 1, and we get y is equal to 5. You take that guy, you throw it at either one of these guys. I definitely go in for the second one, and you find the x. So if y is 5, then x plus 5 instead of y is equal to 8. Subtract off the 5. We get x is equal to 3. So we have our x, we have our y. We write it as a point, 3 comma 5. So x comma y. And that is the solution to our system. Okay. Everybody got a nice headache yet?
Yeah, there, but,
Yep, all right. Okay. Okay. Trying to decide if you want to do next. Totally can't cover the other method in 12 minutes. And if I did, you wouldn't like me. Well,
substitution.
you know what? Honestly, the second method is, in my opinion, easier. I like it more. So I'm just gonna do it, and then I'm gonna do a bunch more as the review for the next class. I think that'll work out nicely. So the other method of solving a system of equations together is the substitution method. So it works by expressing one of the variables in terms of the other, and then substituting it back into the original equation and simplifying it. So it sounds confusing, but all you really do is you take one of your equations, you solve it for one of the variables, I don't care which, you get either x equals or y equals. And then you're like, cool, x equals that, that means the x in the other equation is equal to that. So you swap it out, and then you have one equation with that same variable. So let's work on oh, now I had examples. What is wrong with me? All right. All right. I got a better idea than looking at these examples. I'm going to use the exact same problems that we just did. So you can see the same ones in two different ways. You can see that we get the same answer both ways. It works out nicely. And actually this equation, this system is perfect for it. So again, same exact example. And notice I gave myself less space. It's a good setup. Same exact example. We have a system where it's 3x plus 2y is 19. And we have x plus y is 8. So the substitution method hinges on you taking one of your equations, solving it for one of the variable, and substituting it into the other equation. So you usually find something that's going to work out nicely, like this last term, or this last equation. I could solve for either x or y really easy, right? It doesn't matter which one you solve for. So let's say I solve for x. So I have x plus y is 8. And if I solve for x, I would subtract the y from both sides. And I would have x is equal to 8y, or 8 minus y. There's a minus there, I promise. I'm not rushing. I don't know what you're talking about. So we have 8 minus y is x. That's telling us that this x, this is equal to x. So that's equal to x here and here, right? Now, you always have to substitute it back into the other equation. You can't substitute it into the same equation because you will always, always, always get 0 equals 0 because it's the same damn line. But if you plug it into the other line, so we have this 3x plus 2y is equal to 19. Well, now we're saying that x is equal to 8 minus y. So that x is equal to 8 minus y. So we actually substitute it, put 8 minus y in parentheses instead of that x, and rewrite the rest of it exactly the same. So we have 3 times 8 minus y, which we've said is equal to x, plus 2y is 19. All right, well, how the hell do I solve that? Well, we all have one big ugly thing with y. So I'm going to distribute that 3 through.
Ah,
I get 24 minus 3y plus 2y equals 19. Hey, look, they're like terms now. So I have 24 minus y is 19. If I subtract 24 from both sides, I get negative y is equal to negative 5. So I had to do this again. Divide negative 1 on both sides, and I get y is equal to 5. All right, well, now I got to go back and substitute it for finding x. Well, what I usually do is I already have something in terms of that. I have x equals now. That works out on every single substitution problem. I love it. I have x is equal to 8 minus that. So x is 3. I got my x, I got my y, 3, 5. Same exact answer, two different ways of doing it.
So simple. It's so much simpler than substitution than the,
I know, nobody ever believes me. So
Oh my
many
God.
people tell me,
holy crap.
most people tell me that elimination is easier, and I'm like, man. Like, if I did a bunch of them, it would make a lot more sense. But
That made it so much easier.
there's a lot of guesswork involved. Okay, so what was that other one I did?
Move that up.
Okay, 3x plus y is 5. And 2x minus y is 0. So again, this is the same thing I started out doing the elimination method with, but I'm going to do this with substitution. So again, you want to find something that's going to be easy to solve for, and I am zeroing in on that y right there. Right? If I solve for x, I would have to divide everything else by 3. I would get fractions everywhere. Find something nice. So this one, I'm going to solve for something nice. I'm going to solve for that y. And I have y is equal to 5 minus 3x. You take that, you plug it in for that y. So we're going to have 2x minus, not y, 5 minus 3x. Always put in parentheses, especially in situations like this. Because what ends up happening is that negative, you treat it like a -1, that will distribute in here. You end up with 2x minus 5 plus 3x. That negative, flip the signs on both. Combine like terms, we have 5x minus 5 is 0. Add the 5 over. 5x is 5. Divide off the 5. X is 1. Cool, we have x, we need y. All right. So y is 5 minus 3x. Nope, it's 3 times 1. So y is 5 minus 3. Y is 2. We have our x, we have our y, we have our point. Okay. So that is the substitution method. I have, God, I want to cover more on the elimination method, but hey, it's 8:26. This was random, but I really wanted to cover it because this is useful and it will be on the ISET or DUD. So if this didn't make too much sense, I am going to do more examples on this as the review in the next class. But please, please, please log into Essential Ed, watch those videos, and try to work some of those through as well, because this is trickier than a lot of the stuff we've done, and it gonna melt your brain. And if I melted your brain, my bad. I kind of feel bad about it. Not really. It's my job, but you know, whatever. Yeah. So yeah, there was 2 lessons in 1. I finished one. I made up another one. It was, that was kind of a train wreck, but you know, it worked. Okay, so I will see hopefully all of you back on Thursday for our final class. And if you have any questions or need anything, shoot me an email, let me know. Speak up in class, but none of you are going to do that, let's face it. All right. Have a wonderful night, guys.
Well, I gotta talk to Elizabeth, see what I can do if I can take the test or not.
Okay.
You know, after starting over next on January, then what the hell? So.